So, again the start of the new lecture. We have come a long way from just understanding basic properties of dielectric materials, and then investigating polarizability through simple mechanisms, getting around with the equations of polarizabilities for all three mechanisms, electronic, ionic and dipolar. And then we looked at the frequency response of dielectric, which is the real case of dielectric, because most of the dielectrics are used at certain frequency, and depending upon the frequency of operation, dielectric materials exhibit a typical behavior which is characteristic of these materials, and which is dependent upon the frequency at which they are used. So, in this context we looked at, for instance, the dielectric constant, which was n qi square divided by m epsilon naught multiplied by omega naught I square minus omega square divided by omega naught I square minus omega square plus omega square gamma square. So, this was following the consideration that we were doing analysis for a charged dipole, assuming it to be a linearly mechanically oscillating linear oscillator, and we worked around with the equation of motion to reach this expression, which is the frequency dependent expression for dielectric response specific to electronic and ionic mechanisms. So, you have this frequency dependence of dielectric constants. Now, it could be taken both for, so omega OI would be characteristic for both electronic and ionic, and depending upon the mechanism the magnitude will change. So, when you plot this versus the frequency, so I am just going to plot the high frequency part. So, if you plot epsilon prime versus, let us say, let us not confuse, so let us just write omega. So, it was something like that. Okay, it is not the most precisely drawn. Let me just draw it a little bit more precisely. Okay, so this was omega O electronic, and this was omega O ionic. So, of course, omega O electronic is higher than omega OI, because the entities involved in terms of oscillation are lighter. We are talking of oscillation of electrons with respect to nuclei in an atom itself, whereas we are here in case of ionic mechanism we are talking of oscillation of two different ions with respect to each other. So, nevertheless, what they undergo is a phenomena called as resonance, and this characteristic frequency is the resonant frequency, where charges oscillate together with the applied field. So, they are in resonance with the applied field, and if you plot epsilon r double prime, this shows a loss at these frequencies. So, this undergoes a maxima in the loss characteristic maxima. So, this is when they absorb maximum energy. As a result, the loss is maximum. So, this is typical of these two mechanisms, where you can consider a charged dipole as a linear oscillator. However, when you go to high frequencies, at high frequencies we encountered another term called as relaxation, and that relaxation was nothing but when you have now this happens in polar materials, and polar materials are typically molecules of big groups of atoms. Now, these group of atoms, when they go from one position to another, whether upon the application of electric field or when a field is released, they find, so they stay at position 1, and from going to position 1 to position 2 to position 3, which are all statistically equivalent position, they find they encounter a barrier for their migration. As a result, this is a temperature dependent phenomena, and they require time because it is a long range movement. So, as a result, or instead of calling it long range movement, let us say it is a energy assisted process. So, they do not tend to move, rather they tend to relax in the statistically equivalent position. So, this phenomena here it is called as relaxation. So, and this relaxation we looked at the relaxation equation, and that relaxation equation was given as, and we looked for that we considered what is called as a dipole stable model, bistable model, and that relaxation equation we said was dPd by dt into tau plus Pd, that was equal to Ps, and this is based on this plot. So, if you make a plot of polarization versus time, so you have an instantaneous polarization. So, this is P instantaneous, and this develops into Ps in a time dependent fashion. So, this is the saturation polarization, and polarization at any given point of time between these two stages is time dependent polarization, and this is because of need and so because of need of the molecules or the group of atoms to move from one position to another in a time dependent fashion, because they are heavier groups. And when you remove the field, they of course the molecules relax back from Ps to 0, and this P instantaneous is nothing but sum of ionic and plus electronic, and these two are almost instantaneous because they take place at very high frequencies. Now, the formalism and so we worked around this formalism, and what we got here was which we defined as Debye equation, and these Debye equation led us to solution of above relaxation equation leads us to what is called as epsilon r infinity plus epsilon rs minus epsilon r infinity divided by 1 plus I omega t. Okay. And from this you can also determine what is epsilon r, since epsilon r star is equal to epsilon r prime minus I epsilon r double prime. You can break this up, and what we determine from this is epsilon r prime to be equal to epsilon r infinity plus epsilon rs minus epsilon r infinity divided by 1 plus omega square tau square, where tau is the relaxation time. Okay. And subsequently you can also do epsilon r double prime, that was omega tau divided by 1 plus omega square tau square multiplied by epsilon rs minus epsilon r infinity, where epsilon rs is the static dielectric constant at low frequencies and epsilon r infinity is the static dielectric constant at high frequencies, which means rs is below the dipolar polarization frequencies and r infinity is above the dipolar polarization frequencies, that is into the ionic and electronic polarization range. And this gave us to these equations are called as Debye equations, and these are very fundamental to study of dielectric materials, because they characterize the response of dielectric constant for a ideal dielectric material under the influence of frequency. So, when you plot this dielectric constant, it goes, so when you plot this as a function of frequency, it undergoes inflection. So, this is epsilon rs, this is epsilon r infinity, this is epsilon r prime, and this frequency will be omega is equal to 1 over tau if the axis was omega, and if you plot correspondingly epsilon r double prime, this shows a maxima at this frequency. Oops. And again, so this is your maxima, and you know from this tan delta is equal to epsilon r double prime by epsilon r prime, which can again be plotted, which would be shifted slightly towards. So, if you plot tan delta, it would be shifted slightly towards higher frequencies. Okay. And then we also saw this that this tau, or the relaxation time, is also dependent upon the what we call as temperature. And from this we saw that this was equal to exponential of QA by KT, where tau naught is the intrinsic relaxation time, and QA is the activation energy, which is same as that we discussed earlier, EA for the dipole relaxation. Okay. So, you can terminology changes from QA to EA to whatever, but the meaning does not change. And this activation, this relaxation time is, as you can see, is temperature dependent. So, as the temperature increases, this relaxation time would decrease, which means the frequency will increase. So, as we discussed last time, for taking the example of glass ceramic, when you plot tan delta versus frequency, as you increase the temperature, the maxima in the tan delta shifts towards higher frequency, and that is explained by this activated behavior of dielectric constant, relaxation time of the dielectric materials. And so, the overall picture is now pretty much clear. So, this is something like, so if you plot epsilon r prime, it looks like this. So, this is pertaining to electronic, this is pertaining to ionic, and this is pertaining to relaxation. So, this is given as omega O I, this is given as omega O E or E L, and this is nothing but 1 over tau. And again, just to reiterate, these are resonance related phenomena, these two, and this is relaxation. This is the crucial difference between dielectric behavior at various frequencies, and corresponding loss goes through maxima at this point, maxima here, then and then maxima here. Okay. So, this is your epsilon r double prime. So, this sort of completes a discussion on the behavior of dielectric materials under the influence of alternating field. Now, the question is, we know what the behavior theoretically is, but how do we measure, how do we characterize them practically? Now, this is something which is not so easy, it's a little bit tricky, because when you look at the dielectric material, so dielectric material is used like this. You have a dielectric material. So, this is your material. This material, it is not always single crystal, which means it can be polycrystal. If it is a polycrystalline material, then it has things like grain boundaries. Let us say these are grain boundaries. These are grains, and depending upon the grain size and the nature of grain boundaries, these grain and grain boundaries act quite differently in dielectric materials, which means the electrical response of charges under the application of electric field in grain boundaries and in the grains is very different from each other. Moreover, you can also have defects like porosity. So, this is, let us say, porosity. These are microstructural features. On top of that, you cannot make a dielectric measurement without putting a contact on it, which means I need to put a contact. Let us say this is a metal contact. So, these are nothing but your metal contacts, which are often called as, technically they are called as electrodes, and these two are connected to an electrical circuit where you apply the field. Now, not only you have polarization mechanisms when you apply field, not only you have polarization mechanisms active in the dielectric material. So you are looking at contributions to dielectric constant from material, and material will mean grain, it would mean grain boundary, and it would also mean electrode, material, interface. Electrode is a, suppose if electrode is made of a good metal, electrode will not contribute to any capacitance. So, but the significant contribution comes from the space charge accumulation or the nature of this interface. So, this interface, nature of this interface is extremely important in evaluation of real dielectric constant of the material. So, when you have dielectric constant which is being which has contributions from the material itself, apart from that you have contribution from the electrode material interface as well, and host of other sources such as the leads, etc., and the equipment which you are measuring, that itself will have its own inbuilt impedance which gives rise to capacitance. So, the question is how to separate these. So, the subsequent part of this lecture is devoted towards building an understanding of how we are going to do that, what are the best possible methods that are available to do this. So, the first thing in this regard is what we discuss is, let us take the case of an ideal dielectric material. Okay. So, we start with the ideal. So, what we can do is that we can electrically describe this dielectric material So, as a part of this electrical description of dielectric material, it has been shown that an ideal dielectric material can be represented by a equivalent RC parallel circuit. So, this is RC So, what you have here is equivalent, a perfect dielectric material looks as hypothesized by Debye. It looks something like this. It is made up of a capacitor and an RC element. So, R and C are in series, which are parallel to another capacitor. So, let us say this is C1, this is C2 and this is R2. So, this is how an ideal dielectric material looks like. Now, how do we know that this looks like an ideal material? We need to analyze the admittance of this circuit. Once we get a feeling of admittance, once we get an expression of admittance of this circuit, we relate it to the expression for ideal dielectric material with the frequency term in there, and then compare both the equations whether we arrive the Debye equations or not. So, we will, as we will see, that we will arrive at the Debye equations, but how? Let us see that. Okay. So, let us consider this circuit that just now we have drawn. So, you have a C1 capacitor which is in parallel with RC element R2 C2 which are in series with each other. So, C1 is parallel to R2 C2. So, admittance, let us define as admittance Z, this is inverse of, let us say, impedance. Impedance is nothing but, as you can understand from these term itself, impedance means the overall resistance of the material. Admittance is nothing but something which is related to admitting. So, admittance is nothing but really opposite to inverse of impedance. So, this Y, this is sorry, I have written this Z wrong here, just make a correction, this should be Y. So, Y is equal to 1 divided by Z overall impedance, and what is this Z? Now, we are looking at two parallel elements, one is the C1, another is the C2, R2 C2. So, this would be nothing but 1 over Z1 plus 1 over Z2. Okay. So, what is Z1? Z1 is nothing but 1 over I omega C1 pertaining to element C1 and Z2 can be written as 1 over I omega C2 plus R2. Okay. So, these are the two expressions for Z1 and Z2. Now, admittance will be equal to, so admittance, so 1 over Y is equal to 1 over Z1, which means 1 over 1 divided by I omega C1, okay, plus 1 divided by R2 plus I omega, sorry, just this is Y, and that is equal to 1 by Z, and this is so R2 plus I omega C2. Okay. And this can be rewritten as I omega C1 plus R2 plus, let us not write that, let us just leave it in this form, 1 divided by R2 plus 1 over I omega C2. Okay. So, this is the expression for admittance that we get from just by putting the two impedances together. Now, when you apply an alternating field to the capacitor, such a circuit, then capacitor goes cycles of, depending upon the so waveform is something like this. If your waveform is like this, then as a result of the nature of this waveform, your capacitor will charge and discharge and charge and discharge. Now, so based on that, if you apply this to the R2 C2 element, so you have C2 C1 C2 R2. So, here what happens is this capacitor C2 charges through this resistor R2. Now, what we need to do is that suppose we apply a field to this particular segment, we can apply what we call as Kirchhoff's law to this segment. So, if we apply Kirchhoff's law, now Kirchhoff's law is a very basic law in physics that you know from your 12th standard. So, if you apply Kirchhoff's law to this segment, then what it says is that the sum of two currents, the current due to current in capacitor and the current in or the current due to current in capacitor must be equal to the current in the resistor, which means I need to if I need to apply Kirchhoff's law, then C2 multiplied by dV by dt, which is the current term for capacitor, and this is nothing but your so how do you get to this term, because you know that Q2 is equal to C2 V2, okay, and when you so the current in capacitor would be dQ2 by dt2, so this is I C2 will be equal to C2 dV2 by dt. So, C2 just a mistake, this is C2V, let us not write V2. Okay. So, C2 dV by dt, the current in the capacitor plus the current through the resistor, which is V divided by R2, this is simple Ohm's law, is equal to 0. This is your Kirchhoff's law. Now, this is simple linear differential equation. If you solve this equation, what you come across is V is equal to V naught exponential of minus T divided by R2 C2, where V naught is the voltage at T is equal to 0. So, if V naught is the voltage at T is equal to 0, R2 C2, which is in the exponential term, must have the same units as of time, and this R2 C2 is defined as tau 2, which is called as time constant, okay, and this time constant is basically the time which is needed. So, this is nothing but equivalent to time needed for the voltage to drop to a value V naught by E, okay, which comes out to approximately 36.8% of V naught, okay. So or 0.368 of V naught. So tau 2 basically is the time tau 2, which is R2C2, is the time which is required to charge the capacitor through the resistor, okay. So you are charging the capacitor through the resistor. So time which is required to charge the capacitor through the resistor to a value 1 minus 1 by E, that works out to 63.2% of its full charge, okay. So that is one definition. So time tau 2 is the time which is needed to charge the capacitor C2 through resistor R2 to a value 63.2% of its full charge, or the time which is needed to bring the voltage down from V naught to V naught divided by E, which means to discharge the capacitor to 36.8% of its initial value. So both are equivalent. Either you charge it to 63.2% of full charge, or you discharge it to 36.8% of the initial value. So whether you, it's like holding same thing in two different ways, saying same thing in two different ways. So this is tau 2. So tau 2, from this we have, so this is now what we do is that we make use of this term and insert this in the impedance or admittance equation that we earlier worked out. So insert tau 2 in admittance equation. When you do that, what you get is y is equal to I omega C1 plus what I had there was R2 C2. So I had was let me write the original expression. So what I had was R2 plus 1 over I omega C2. So what I am going to do is that I am going to multiply by C2, okay, and multiplied by C2 here. So this becomes tau 2 and these cancel each other. So what becomes, this is I omega C1 plus C2 divided by tau 2 plus 1 divided by I omega, okay. Now you can further rework this equation, and what we get in the modified form is y is equal to omega square tau 2 C2 divided by 1 plus omega square tau 2 square plus I omega multiplied by C1 plus C2 divided by 1 plus omega square tau 2 square, okay. So this is the expression for admittance. Now from the previous expression, if you remember in this module itself, when we worked out the circuit for or let us say the representation of dielectric material using the under the influence of alternating field, we came across an expression for charging current IC, that was nothing but I epsilon r prime plus epsilon r double prime multiplied by C naught omega V, okay. And if you take this here, IC divided by V, this becomes equal to I epsilon r prime plus epsilon r double prime multiplied by C omega. And what is IC by V, which is nothing but 1 divided by, so IC by V is nothing but 1 divided by Z, and this is nothing but admittance, So y is equal to I epsilon r prime plus epsilon r double prime multiplied by omega naught, sorry, omega c naught. Now you compare this equation with this equation, and what I am going to do, what we are going to do is that all we are going to do from that, as you can see, is to get expressions for epsilon r prime and epsilon r double prime. Okay. And if you do that, then so upon comparison, what we get is epsilon r double prime to be equal to C2 divided by C naught multiplied by omega tau 2 into 1 plus omega square tau 2 square, and epsilon r prime is equal to C1 divided by C naught plus C2 divided by C naught multiplied by 1 divided by 1 plus omega square tau 2 square. Now, if you compare these with the Debye equations, which is, if you compare these with the Debye equations, they are fairly similar. You can write the Debye's equation parallelly and make a comparison. Upon comparison, what you will find is that these two equations are similar, very similar, with C2 happening to be equal to epsilon rs minus epsilon r infinity multiplied by C naught, and C1 happening to be epsilon r infinity. So, if this upon this condition, those two equations which we have seen on the last slide are nothing but your Debye equations. So, this gives us a very nice way of modeling a dielectric material as an electrical circuit. So, basically, if you rewrite these, epsilon r double prime is equal to epsilon rs minus epsilon r infinity divided by multiplied by C naught divided by C naught into omega tau 2 divided by 1 plus omega tau 2 square, and C naught cancel each other. So, what you get is epsilon rs minus epsilon r infinity into omega tau 2 divided by 1 plus omega square tau 2 square. Similarly, for epsilon r prime, C1 divided by C naught, which is epsilon rs minus epsilon r infinity plus C2 divided by C naught, excuse me, it's other way around, it's C1 divided by C naught. So, this is epsilon r infinity plus epsilon rs minus epsilon r infinity divided by 1 plus omega square tau 2 square. So, upon making the comparison, now the circuit looks like this. Okay. So, this is your R2, this is your C2, this is your C1. So, the C1 is nothing but epsilon r infinity, C2 is nothing but epsilon rs minus epsilon r infinity multiplied by C naught. Okay. So, now you can see how does this dielectric material look like. It looks like an electrical circuit of this type, where C1 and C2 can be defined in terms of differences. Either C1 is nothing but your high frequency static dielectric constant, and C2 is nothing but the difference between low frequency and high frequency dielectric constant in series with the resistance R2, okay, which is the resistance of the material. Okay. So, this behavior gives an opportunity to describe the behavior of dielectric material in an electrical circuit, which can be modeled easily, and based on this behavior, there have been several attempts to characterize and understand the electrical and microstructural and relate it to microstructure and defect behavior of dielectric materials. And in this regard, in 1941, two brothers, two scientists, K. H. Cole and R. H. Cole, Kenneth Cole and Richard Cole, they explained the behavior of dielectric materials in the alternating fields by plotting the real and imaginary parts of these two impedances, which are nowadays being used in terms like impedance spectroscopy. So, what they got was, if these two materials exhibit like a perfect material, then for a perfect material the dielectric response, if you plot the imaginary part versus the real part, then they should represent a perfect semicircle. It does not look like perfect here. So, let me just try to draw as perfect as possible. Okay. And this is with increasing frequency. So, so this should look like an ideal half circle, and this would mean an ideal. So basically I want to say half circle would, a perfect half circle would represent the response of an ideal dielectric material. And here, as you can see, these two intercepts on the x axis would mean the values of dielectric constants, and if you just if I just write it slightly away so that it does not get confusing, epsilon r prime. So, this value becomes epsilon prime r s, which is the because we are increasing the frequency in this direction, a static dielectric constant, and this becomes your so, or alternatingly in terms of electrical circuit, this becomes equal to C 1 plus C 2 divided by epsilon naught, and this becomes or C naught, you can say, depending on how you say it, and this intercept becomes C 1 divided by epsilon naught, or you can write it epsilon r s epsilon r infinity. Okay. So, this is the high frequency part, this is the low frequency part, and the difference between these two is the epsilon r s minus epsilon r s minus epsilon r s infinity, and the circle of, and this circle. So, the diameter of this circle would be diameter of this circle would be, as you can see from here, would be epsilon r s minus epsilon r infinity. This will be the diameter of this circle. So, a perfect dielectric material, as Kenneth and Richard Cole proposed, would look like a perfect half circle when you plot epsilon r epsilon double prime with respect to epsilon prime as a function of frequency. However, this is true only for materials which exhibit ideal behavior. In case of non-ideal behavior, this Debye equation gets modified according as Kenneth and Richard Cole showed, and that we will so that we will just write in a minute. So, now this, as we said, that if you have a perfect semicircle, this means this represents the behavior of perfect dielectric material. Now, any deviation from this perfect semicircle is going to lead to deviation from ideal behavior, which can be related to various atomic and microstructural features of the material. So, for a non-ideal material, Cole, both Cole brothers, Cole and Cole, they modified the Debye equation. So, by the way, let us just go to previous page, and this is called as Cole plot, and this goes after RH coal and KS coal 1941. There are papers online which you can go through them. So, modified this equation. So, this becomes now epsilon r star minus epsilon r infinity divided by epsilon r s minus epsilon r infinity, and this becomes equal to 1 plus I omega tau to the power 1 minus alpha. So, this is the modified Debye equation, where alpha is a parameter which takes care of non-ideality, and that since that and this non-ideality is effectively represented in terms of a variety of relaxation time. So, you do not have a single relaxation time, what rather you have many relaxation mechanisms which have their own relaxation times. So, this alpha describes parameter describing the relaxation distribution or relaxation time distribution in the material. Okay. So, naturally, as you can see, for an ideal material, this alpha would be equal to 0 and system would be characterized perfectly by the Debye equations which we just now saw. And if you plot epsilon r prime versus epsilon r double prime as a function of frequency, you should get a perfect semicircle. So, perfect semicircle, and maxima naturally will occur. So, this corresponds to maxima in epsilon r double prime, and you know this happens at omega is equal to 1 by tau, or where omega tau is equal to 1, and so this is the wave frequency is changing. So, this is your epsilon r s, and this is your epsilon r infinity. Okay. And this way of characterizing the dielectric materials is called as impedance spectroscopy, and, and you can do this by using techniques like impedance analyzers, which work very well to characterize these materials. So, all you do is that you measure the real and imaginary part of the impedance related to the dielectric constant from the equations that we have seen earlier, and and then make a plot to see whether you have an ideal behavior or not. So, if you have an ideal behavior, again I am going to plot epsilon r omega versus epsilon r prime omega. So, imaginary versus real part, and if you have ideal circle, so this should be your epsilon r s, epsilon r infinity. This happens at omega tau is equal to 1, and as you know, the diameter of the circle you can see it is nothing but difference of these two dielectric constants. So, this semicircle is represented by, so you know what is the semicircle equation is. Semicircle equation is nothing but x minus r square plus y square is equal to r square. So, you know that r here is nothing but epsilon r s prime minus epsilon r infinity prime divided by 2, diameter divided by 2, and x and y you can plot from. So, this is x and this would be y, and so this can be represented by the semicircle equation, which is epsilon r minus half of epsilon r s prime minus epsilon r infinity prime to the whole square. Oops. So, x minus r square plus y square epsilon r omega square, and that is equal to r square, which is epsilon r s minus epsilon r infinity square divided by 4. So, this is your semicircle equation. Often what you see in reality, that you do not get a semicircle, and you get a semicircle like this with a tail, and this tail often represents high losses in the material or distribution in the so if you have a this dashed line on the low frequency side. So, this is low so frequency goes like this. So, this is low frequency, this is high frequency, and if you have a tail, this tail indicates high losses. So, basically what it means is that at the low frequency your epsilon r double prime is very high, which means material is very lossy. Another thing that you see often is you do not have one semicircle. What you have is you have a range of semicircles. So, you have semicircle like this, like that. When you have such kind of phenomena present, then what happens is material has contributions coming from more than one mechanism. So, what may happen is in such a scenario, the material exhibits contributions from the grain boundary and from the electrode ceramic interface. So, this is typically your electrode ceramic interface. This would be your grain boundary, and this would be your grain. And as you see, since we are so this is epsilon r prime and this is epsilon r double prime. So, you need to make a circuit for this, you need to make a circuit for this, and you need to make a circuit for this. So, basically what it means is that you have three circuits running parallelly in series. So, one would be corresponding to grain, another would correspond to grain boundary, another would correspond to electrode ceramic. And as you can see from the frequency, this should occur at the lowest frequency, this should occur at the middle frequency, and grain should show the bulk effect at the high frequency. So, if you have these multiple mechanisms present in the materials, then you would encounter more than one semicircle. Very rarely you will encounter a perfect semicircle. Often these semicircles are also overlapping with each other. So, you need to model them properly in order to analyze the effect of each and every contribution, which is a completely different subject altogether, and this subject is known as impedance spectroscopy. So, basically it is a tool to characterize the dielectric materials nicely and to understand the behavior of these dielectric materials under the alternating field and to extract the contributions to the dielectric constants from various segments individually. So, this is a technique which is a very powerful technique. It is a very detailed technique, we cannot unfortunately go in this course, but all I wanted to say is that if you plot this real and imaginary part of dielectric constant or nothing but which is nothing but extracted from the impedance data, then you can get these semicircles which can be effectively used to characterize the dielectric material. So, this takes us to the end of this module, which is finally now. So, we have discussed what dielectric materials are, what various polarization mechanisms are. We have looked at the polarizability through simple formalisms, analytical treatment, and then effect of frequency, to look at the resonance and relaxation phenomena, and then finally how do we characterize or how is the dielectric behavior characterized really, and that we see that by presence of semicircle or ideal or non-ideal, you can distinguish between various contributions that make to the dielectric constant in the dielectric material. Finally, the final content of this module is how the dielectric. So, dielectric materials work long, but they do fail, as you can see in the poles, electricity poles, that you see often sparking takes place and the capacitor which is put around the pole, that suddenly gets bursted or there is a fire. So, you see that capacitors fail. So, this failure of capacitor failure is called as dielectric breakdown, and this is nothing but, so when you plot this I versus V or I versus E, there is a very small amount of current that flows up to a critical field, and when you reach a critical field there is sudden jump in the current, and this is nothing but your failure or breakdown. So, this is called as critical voltage or field. So, beyond, so there is a critical voltage for these materials, which if crossed these materials fail, and there are variety of mechanisms which are proposed to explain these failures. So, these failures are often you divide them in two categories. One is the intrinsic mechanisms, and these intrinsic mechanisms are nothing but your defined as or rather intrinsic or basic mechanisms. So, one is called as intrinsic breakdown, then you have thermal breakdown. Instead of intrinsic, let us call it primary, okay, primary mechanisms, because these two intrinsic clash with each other, and then you have avalanche breakdown, and then you have what is called as secondary and in case of secondary mechanisms you have dielectric discharge, and or you can say mechanical breakdown or electrochemical breakdown. So, we will not go into details of this breakdown mechanisms, we will just go through very casually what this means is. So, in case of intrinsic breakdown, what it simply means is that this mechanism is based on lattice ionization. So, and what this means is that basically as you keep applying the field, the lattice gets ionized, and this subsequently increases the electron temperature, and this electron temperature, once it reaches the critical field value, corresponds to the critical field value, the failure occurs, and this is characterized by large increase in the current in the material, and this process the process break time is very short, and this as a result this process is very quick, and this process is also electronic in nature. So, basically what it means is that you have conduction band, you have valence band. So, basically you make enough electrons to go into conduction band, so that the material become conducting. So, and that critical field will correspond to what is called as the band gap of the material. And then second mechanism is thermal breakdown. So, here you can also add increase in electron temperature as a function of field. Okay. As you increase the field, the electron temperature increases. In case of thermal breakdown, what happens is that this occurs due to heat dissipation. And this is basically due to current flow that is happening in the defective parts of the sample, which in turn increase and those defects could be ionic defects, lattice defects, etc. And as a result, the material has a resistance which leads to or material has some conduction, and this long range conduction leads to heat dissipation, and this is a very common process in the bulk materials. It observed at temperatures between room temperature to 300 degree 400 degree centigrade, and typically here the rate at which you apply the field is a very important factor, and this process can be slow since it takes time to build up for the heat to build up, and this the time range varies from milliseconds to few minutes, and it also depends upon sample geometry, because sample geometry will determine how the heat is dissipated out of the sample. So, essentially it is basically because of increase in temperature of the sample, which is thermal, not the electron temperature, but the real temperature. And the third is called as avalanche breakdown. And avalanche, as the name suggests itself, a few electron get sufficient energy by application of high fields, and these high energy electrons knock off many other electrons in the lattice, thereby increasing the conductivity of the material. So, basically due to multiplication of carriers by collision. So, high energy electrons knock off many more electrons from the conduction from the lattice, and this multiplication in the electron numbers leads to increase in the conductivity, which leads to eventually the failure, and this happens typically in thin films. And this is a process which occurs at lower temperature, and it is very fast process, very short time process. And then finally, secondary mechanisms are your local discharge or dielectric discharge, and this is due to presence of defects such as porosities or entrapped gases. So, when you have this porosity and entrapped gases, these gases gets ionized inside this. So, inside these pores and defects, and due to ionization of these defects, they suddenly explode inside the dielectric material, leading to local discharge. And as you can see, this is characterized by some sort of sparking in the material as well. So, this is typically due to microscopic pores. And then finally, we have what we called as electrochemical background, electrochemical or mechanical breakdown, and this is essentially due to transport of conducting material because of local electrochemical current paths that may be created inside the material in the interior of dielectric, and basically due to presence of local electrochemical paths, and these are affected by atmospheric conditions such as humidity and pH. So, we finished this module here. In summary, what we have looked at is the behavior of dielectric materials. Started with fundamental properties, looked at the polarization mechanisms. Then polarization mechanism is characterized by what is called as polarizability, which is a microscopic property. We tried to get analysis of this microscopic property just by looking at simple analytical treatment without using the frequency, and then we looked at the behavior of these dielectric materials in the presence of frequency to get a real picture. And finally, we looked at how the behavior of these materials can be modeled and how can they be studied by using techniques like impedance spectroscopy, thanks to the efforts of coal scientists who developed a nice method to study these materials. And then finally, we looked at some of the breakdown mechanisms of dielectric materials. So, this finishes this module here. In the next module, we will look at special dielectric materials which are different from what we have studied so far, and we will take them further in the next class. Thank you.